And for the first talk this afternoon, we are happy to have Professor Zhouli Xu from UCSD and UCLA. Professor Xu is a leading expert in stable homotopy theory. Together with his collaborators, they establish surprising connection between algebraic geometry and homotopy theory, leading to a new approach to compute stable homotopy group of spheres and solve several long-standing problems. Professor Xu will give us two talks this afternoon, and the title of the first talk is Homotopy Group of Spheres. Let's welcome.
Thank you very much for the introduction. It's a great pleasure to be here, and also thank you everyone for coming to my talk. So I'm going to talk about a topic in algebraic topology, namely homotopy groups of spheres. So here's the outline of my talk. So for the first part, I will start with a story in geometry, namely the classification problem of smooth structures on spheres. So this is a rather old connection due to Kervaire-Milnor, and they reduced this problem of counting smooth structures on spheres into the problem of computing stable homotopy groups of spheres in algebraic topology, and another problem called the Kervaire invariant problem. So I will first talk about this part, and in the second part, I will survey on some classical methods of computing stable homotopy groups of spheres. And then in the third part, I will talk about a more recent method, namely the one using motivic homotopy theory. So motivic homotopy theory is a theory introduced by Wolski and Morel, trying to use abstract homotopy theory to study problems in number theory and algebraic geometry, and it was very successful. For example, in Wolski's proof of the block-cutoff conjectures and Billingson-Lindenstraum conjectures and so forth. So with my collaborators, we realized that we can reverse the information flow and reuse the motivic homotopy theory to study problems in classical topology. Okay. So I will talk about that, and if there is still some time in the end, I will talk about some future directions. All right, so let me start with this Poincaré conjecture or Poincaré's problem. So the question by Poincaré in 1904 asks, if M is a closed manifold, so closed here means it's compact and has no boundary, and is of dimension 3, and moreover, pi 0 of M and pi 1 M are both 0, so it's path connected and is simply connected. And the question is M homeomorphic to the 3 sphere? So as we all know, the answer is yes. This is proved by Pellerman in 2002-2003 using geometric analytical methods. But just for the statement of Pellerman's theorem, let's think about this condition: pi 1m and pi 0m and pi 1m are both 0 for closed 3-dimensional manifold. So if you think about it, you realize that this condition is the same as stating that this manifold is homotopy equivalent to the 3 sphere. So being homotopy equivalent to the 3 sphere is a equivalence relation, but a weaker one compared to being homeomorphic to the 3 sphere. So one way to understand the statement is that this weaker equivalence relation being homotopy equivalent to the 3 sphere actually implies the stronger equivalence relation, namely being homeomorphic to the 3 sphere. So of course, we don't have to ask this question just in dimension 3. We can ask this question in all dimensions. So if you take an n-dimensional manifold which is closed, and it is homotopy equivalent to the n sphere, we could ask, is M actually homeomorphic to the n sphere? So does the weaker equivalence relation actually also implies the stronger one in other dimensions? So for dimension 1 and 2, it's not hard to see this is the case, and it turns out the answer is yes for all dimensions. So the dimension 4 case is proved by Friedman in the 80s, and the dimension at least 5 is proved by Smeyer, Newman, Cornels in the 60s. So the version Smeyer proved requires this manifold to have a smooth structure to start with. So summary here is that in all dimensions, being homotopy equivalent to the n sphere actually implies being homeomorphic to the n sphere. So if we're talking about manifolds and it could have a smooth structure, maybe in the smooth category, there are more equivalence relations. Namely, we could be talking about diffeomorphic to the n sphere. So this is the generalized smooth Poincaré conjecture. So namely, if we start with a closed n-dimensional manifold which already has a smooth structure, and its underlying topological space is an n sphere, we could ask, is M diffeomorphic to the standard n sphere sitting inside of Rn plus 1. So in other words, we're asking whether or not this topological sphere could admit exotic smooth structure, which is different from the standard one. So again, in dimension 1 and 2, the answer is yes. It turns out the dimension 3 case was known a long time ago. It's due to Moyes in the 50s. So in fact, every topological 3 manifold admits a smooth structure and it is unique. So in particular, the 3 sphere has a unique smooth structure. So the dimension 4 case is, of course, wildly open. This is known as the smooth Poincare conjecture in dimension 4. If you want to know more about what happens to this conjecture, you should ask Tripper in the audience. And all right, so I won't say anything about that. For higher dimension, it turns out in dimension 5 and 6, the answer is still yes. There is a unique smooth structure on these two spheres, and this is the work due to Kervaire and Milner. So in fact, Milner discovered this exotic 7th sphere. So on the 7th sphere, there is an exotic smooth structure, and later on, Kervaire and Milner computed that there are exactly 28 different smooth structures. And there are some group structures to it, so I'll say a little bit about that later. So in fact, Kervaire and Milner realized that this phenomena of the existence of exotic smooth structures happens quite generally in high dimensions. So having that in mind, we could ask more questions. So first one could be, in which dimensions there is still a unique smooth structure? Or we could ask, if we fix the dimension, how many smooth structures are there? So Kervaire and Milner answered the second question in the following sense. So we always assume n is at least 5. So let's say the n denote the set of all the smooth structure on the n sphere. So it turns out there is a group operation, namely the connected sum. We just cut an open disk on both spheres, and we just put them together, you get another sphere. So by the theorem of Snare, this is the same thing as H cobordism classes of homotopy n spheres. So homotopy n spheres are just the n manifolds that are homotopy equivalent to the n sphere. So cobordism means there's a manifold one dimension higher whose boundary are the disjoint union of these two spheres. And H here stands for homotopy, which requires the inclusion of the two boundaries is a homotopy equivalent. So wanting to know how many smooth structures are there is the same thing as knowing the order of this group, which by the way is always a finite abelian group. There is a subgroup, which I denoted by theta and BP, is the homotopy spheres that bound parallelizable manifolds. So parallelizable just means tangent bundle has a trivialization, it's trivial. And here's a summary of Kervaire and Milner theorem. So first of all, this subgroup is always a cyclic group, and we completely understand the order of this group up to a factor of 2. So when n is even, this group is always a trivial group. When n is 4k plus 1, this group either has order 1 or order 2. When n is 4k minus 1, the order of this group has something to do with the balloon numbers. Okay, so it's this expression here, and for the purpose of this talk, we just know that this number could be very big and it grows very fast. For example, when n is 7, this number is 28, and when n is 15, I think it's 16,000 or something. 16,000 plus change. Okay. All right. So I understand almost everything about the order of the subgroup. So how do we connect to the big group? Well, there is a short exact sequence. Okay. So this is the subgroup. This is the group of all the smooth structure on the n sphere, and their difference is something called pi n mod j. So pi n here, which I will define later, is the nth stable homotopy groups of spheres. So this is something can be defined purely algebraically, or topologically, but computed algebraically. And there's also this j part. So this is the j homomorphism. It comes from the nth homotopy group of the infinite dimensional special orthogonal group mapping into the nth stable homotopy groups of spheres. It is actually a splitting summand. So for the context, this is the j part is the easy part of the stable homotopy groups of spheres, and this co-kernel part is a harder part. So in summary, wanting to know how many smooth structure on the n sphere is so we already know the order of the subgroup, and then they reduce this question into computation in algebraic topology. So this is what happens when n does not congruent to 2 mod 4. So when n does congruent to 2 mod 4, it's slightly more complicated. We still have the first 3 terms in this exact sequence, but there are 2 more terms. So there's a map here. There's a group homomorphism to Z mod 2. This is known as the Kervaire invariant. And then there's a map to the subgroup in one dimension lower. So if you think about it, every group homomorphism to Z mod 2, there's only two possibilities. It's either that it's a surjective map or everything maps to 0. So in either case, we understand the order of this group. So this is the ambiguity of the factor of 2 in the previous slides. So therefore, combining all dimensions, so Kervaire-Müller reduced the classification of smooth structures on n-sphere into two problems. One is computing the co-kernel J part of the stable homotopy groups of spheres. The other one is the Kervaire invariant, namely in which dimensions this map is non-zero. Okay, so it turns out this Kervaire invariant problem also have a geometric background, geometric story to it. So I'm going to take a small digression and talk about the Kervaire invariant problem. So the Kervaire invariant is defined for frame manifolds in dimension 4k plus 2. By framed, I mean there's a framing on the stable normal bundle when we embed this manifold into higher and higher dimensional Euclidean space. So in one sentence, the Kervaire invariant can be defined as the following. It is the Hopf invariant of the quadratic refinement of the intersection pairing with Z mod 2 coefficients. So let me unpack this definition a little bit. So if you take the Z mod 2 coefficient and we take the middle dimension homology, so we know that we have a intersection pairing. So this is a non-degenerate bilinear form over this field Z mod 2. Okay, and quadratic refinement of this bilinear form is a quadratic form which satisfies this relation. And the existence of this quadratic form comes from the framing. So the Hopf invariant is something purely algebraic. Okay, it's an invariant that classifies isomorphic classes of non-singular quadratic forms over F2. Okay, so if you just fix the dimension of the quadratic form which is defined, which is the vector space over F2, and there's an invariant taking value in 0 and 1, so these two things will determine the isomorphic classes of non-singular quadratic forms over F2. So one way to define this is the following. So we just plug in all the possible inputs from this vector space over Z mod 2. Due to its non-singularness, the output will have different numbers of values 0 and 1, and the majority will be defined as this invariant. So by the way, according to your brother, he calls this invariant the democratic invariant because of this definition. Okay, so framing, so here means the framing on the stable normal bundle. So if you embed this manifold into Euclidean space, it has a normal bundle. And if you further embed into higher and higher dimensional manifolds, we have a sequence of normal bundles. We require a trivialization of this normal bundle. So by the work of Pontryagin, we know that these stable frame manifolds of dimension n correspond to elements in n stable homotopy group spheres, and this J part corresponds to change of framing. So therefore, this Kervaire invariant can be viewed as a group homomorphism from the co-kernel of J to Z mod 2. So the Kervaire invariant problem asks for in which dimensions there could exist a frame manifold with Kervaire invariant 1. And when that happens, we know that exactly half of the manifold will have Kervaire invariant 1, the other half will have Kervaire invariant 0, because that's a group homomorphism. So in dimension 2, 6, and 14, there exists certain framings on these three manifolds with Kervaire invariant 1. In dimension 10 and 18, Kervaire proved that for all smooth manifolds, frame manifolds, Kervaire invariant is always 0. So by the way, why do we need to care about the Kervaire invariant? Well, there are several reasons. One of them is that it could, so in high dimensional topology, we could try to do surgery to see if we can convert it into a sphere, and the Kervaire invariant is an obstruction class. And another reason is that, so in dimension 10, Kervaire first defined this invariant in a larger category of manifolds. In particular, it doesn't have to be smooth. And Kervaire constructed an example with Kervaire invariant 1. And he also later proved that all smooth manifold in dimension 10 has Kervaire invariant 0. And therefore, in the first time in history, Kervaire find out an example, a topological manifold in dimension 10, which does not emit any smooth structure. So that's another reason why this invariant is interesting. But of course, we now know this phenomenon could happen in dimension as low as dimension 4. But anyways, The next breakthrough in this Kervaire invariant problem is due to Bill Brother, who proves that there exists a free manifold with Kervaire invariant 1 in dimension n, if and only if, first of all, n has to be of the form 2 less than a power of 2. And then there is a certain statement in algebraic topology which has to hold. Okay? So namely, a particular class has to survive in a spectral sequence that converts to the stable homotopy groups of spheres, and therefore also converted this problem, this Kervaire invariant problem, into a computation in algebraic topology. So in particular, the Kervaire invariant has to be 0 in all dimensions if it is not of the form 2 less than a power of 2. So a more recent result, which is announced in 2009 and later published in 2016, a paper in the Annals with more than 200 pages by Hill, Hopf, and Ramno, they prove that this Kervaire invariant could be 1 only in dimensions 2, 6, 14, 30, 62. So these are the first 5 numbers of this form, and possibly 126. So the 126 was not resolved by them. And I should mention that the dimension 30 case, the first 3 cases are rather straightforward. Dimension 30 case is done by Mahorber-Tangara in the 60s, and there is an explicit manifold constructed by John Jones in his thesis in the 70s. And for the dimension 62 case, this is done by Barry Jones Mahorber in the 80s. But the very interesting thing here is, as I mentioned, so this is only a homotopy theoretic proof. So namely, we do know half of the free manifolds in dimension 62 has Kervaire invariant 1, the other half have Kervaire invariant 0. But as of today, no one has been able to construct an explicit manifold with Kervaire invariant 1 in dimension 62. So this is kind of bizarre. And 2 months ago, I announced this result with my two collaborators, Weinan Li and Guozhen Wang. So we resolved the last case. So there exists a manifold with Kervaire invariant 1 in dimension 126. So namely, so only the first 6 could have a Kervaire invariant. Only these 6 dimensions, there exists a manifold with Kervaire invariant 1. So the rough summary here is that in almost most dimensions, this map, this group homomorphism is always 0. There's only a few exceptions. All right. So, by the way, I'm giving another talk after this one. So I will say more details about this dimension 126 story. All right. So let's get back to the original story, namely the smooth structure on the n-sphere. Okay. So one question we could ask is, in which dimensions there is a unique smooth structure? So a necessary condition would be this subgroup has to have order 1 in the first place. Recall that in dimension 4k minus 1, this thing has something to do with the balloon numbers, right? It's a huge number, it increases very fast. So 4k minus 1, there's no chance. And in 4k plus 1, it depends on the Kervaire invariant problem. Namely, we have this longer exact sequence. Okay. So for this subgroup to be order 0, we need this map to be non-zero. Okay. So therefore, the ones in 4k plus 1 could be, this group could be 0 even only if the Kervaire invariant in one dimension higher is non-zero, which gives us a list of candidates. So combining 4k minus 1 and 4k plus 1, these are all the odd dimensions. So the odd dimensional spheres that could have a unique smooth structure are precisely 3 less than a dimension of 2, than a power of 2. So namely 135, 13, 29, 61, and 125. So these are the candidates for all dimensions that could have a unique smooth structure. So 135 were known before. 13 and 29, they're not unique. So this is done in my advisor Peter May in his thesis in the 60s. So in fact, Peter May computed homotopy groups of spheres and know that there are precisely 3 smooth structures on these 2 spheres. So for dimension 125, we still do not know how many smooth structures are there, but we do know it is not unique. So this is done via a comparison with this generalized cohomology theory of spectrum called TMF, which stands for topological module forms. So it can be used to detect certain maps in spheres and realize they're non-zero. So that's roughly the idea. So we know at least it is not unique. And in the remaining case 61, so that's a theorem due to Guozhen Wang and myself, we did a computation in algebraic topology, computed pi 61 is 0, and therefore the 61 sphere has a unique smooth structure. So based on earlier work, Kervaire, Browder, and Hopf, so these are only odd-dimensional spheres. So with a unique smooth structure, only 1, 3, 5, and 61. So you could ask, okay, so that's the story for odd dimensions. What happens to even dimensions? So first of all, we don't have anything for free anymore, right? These groups are always has order 1. So, but based on our computations, we do have a conjecture. So for dimension at least 6, we do not know anything about dimension 4. So only even dimensional spheres with a unique smooth structure are S6, S12, and S56. So these 3 cases are known. The first one due to Kervaire-Milner, this 56 is due to Isaksen recently. And so this conjecture is more about there's no more spheres in this list. So more than 50% of all the even dimensions were ruled out by the work of Barons, Hopkins, Mahauer, and Quigley using something called chromatic homotopy theory. So chromatic homotopy theory is a subject that studies periodic phenomena in the stable homotopy group spheres or in stable homotopy theory in general. So the idea is to construct enough periodic families to cover all the even dimensions. So in the published works, they have done over 50%. So I have some ongoing progress with Barons and others. We are trying to push this method further and try to establish maybe we can even get 100%. All right, so this is the first part of my talk. I'll pause for a second if there are any questions. Yeah. We have a conjecture, yes. I forgot precisely what the growth is, yes. But it's not a good conjecture in any sense. It's just, we only have computation up to like 90 or 100. So it's not, we don't have enough data to have a good guess. That's what I'm gonna say, yeah, but we did make a conjecture. Oh yeah, for sure, yes. But I think the failure of the telescope conjecture made it harder to expect what's gonna happen. Yeah, right. I can say more afterwards, maybe. Yeah, but yeah.
So why is this 3 spheres special?
That's a good question. Yeah, I mean for the odd dimensions, it's more like 3 less than power 2. But these 3, I don't know. Maybe it's an accident or something. I have no good answer for this. Yeah. Right. All right. So homotopy groups of spheres is the kind of mathematics which is very easy to define but very hard to compute. The definition is very straightforward. Let's consider the spaced continuous maps from spheres in dimension n plus k to dimension k, and then we model by homotopy. And that's the definition. So when n is smaller than 0, these groups are always 0. When n is 0, when the 2 spheres have the same dimension, this is integers. And we know exactly what so these are always finite generation abelian groups, and we know especially the rank. So namely, we know the copies of rationals, so which is theorem due to Sayre. Okay. So here's the table of the low-dimensional computations. Okay. So for example, so let me first explain the notation a little bit. So infinity means the copy of z. A dot just means 0. So 2 means z mod 2, 12 means z mod 12. 2 square means z mod 2 plus z mod 2 instead of z mod 4, and so forth. So, for example, if we focus on this column here, so that's the homotopy groups of the circle. It just means all the higher homotopy groups are all 0, correspond to the fact that the universal cover is contractible. There might be some other patterns you can see. So, for example, if you view the next 4 columns, you don't see a 0 at all. In fact, this is a theorem due to Professor Jie here and Bimsa with his collaborators. That so these 4 columns, there's no 0 in this list. Okay. There may be other patterns you can see, but the pattern I want to emphasize is the following. If you look at the diagonal and look to the right, you see each line here, eventually this stabilizes, right? So starting from the diagonal, and then all the groups here are 2, all the groups are here, 2, 24, and 0, and so forth. So this is not an accident. So this is, in fact, a theorem by Friedenthal, which states that when k is large enough, this group only depends on the difference of dimensions. It doesn't depend on it only depends on n, it doesn't depend on k anymore. So we call this the nth stable homotypic groups of spheres, or the nth stem. So Sarah told us these are always finite abelian groups in positive stems. So therefore, due to the classification of finite abelian groups, we can compute one private time and then sum them together. So, but if we combine all the degrees together, it has a richer structure. So first of all, it forms a ring. We take a map which the difference of dimension is L and a map which is M. We compose them. It's L plus M. So this is a commutative ring in the greatest sense. And there are higher products, so namely tilde brackets, matrix tilde brackets, and so forth. If the two consecutive maps, the composite is 0 up to homotopy, so is this one, then we can define some higher products. So when we do these computations, we would like to compute these structures as much as possible. And here's the table for the stable stems. It's a single graded, but this is the table list up to 55. So yeah, so you can see here. So there are some patterns. So for example, there's some group which has an underline here. That's the contribution of the J part. That's the complete understood part, which only happens in dimensions congruent to 0, 1, 3, and 7 mod 8. And you can also see a lot of like random primes showing up. And there are also theorems saying that every prime, like Z mod P, will show up in the stable in the underline part and also in the not underline part. And we also have theorem stating where the first copy of Z mod this prime show up in this table and so forth. And now we have a table in a much larger range. All right, so here's another way of organizing. If you're just focusing on one prime, there's another way of organizing this data. So the J part, roughly speaking, has period 8. Yes. I mean, it's two 8-periodic things then combined together. So the aperiodicity comes from the Bob periodicity. Yes. Okay. All right. So here's another way of organizing this data. So we are looking at prime 2. So each column here corresponds to pi n. So for example, you see a bunch of dots, a bunch of lines. So this is prime 2. So each dot corresponds to a Z mod 2. Okay. And for example, in the first column, there's only one dot that corresponds to the stable pi 1 is Z mod 2. In the second column, there's only one dot that corresponds to the stable pi 2 is Z mod 2. In the third column, there are 3 dots. But they're connected by the straight lines. So instead of 3 copies of Z mod 2, this is actually a Z mod 8. So the vertical lines correspond to group extensions. So you see other lines of positive slopes. So they correspond to certain multiplicative structure. So for example, all the lines of slope 1 means multiplication by this dot h1. Okay? So we have h1 here. So that dot is h1 squared. And this dot would be h1 cubed. And this dot is, so vertical lines means multiplication by 2, or h0. So this dot is h2, that's twice h2, that's 4 times h2. And it goes to the same dot. That means there's a relation in this ring structure. Namely, h1 cubed equals to 4 times h2. So this is a way to visualize part of the ring structure. And okay, so the J part I was telling you about corresponds to, roughly speaking, this part. So you see this picture. I haven't told you what the vertical line axis means. I'll say that in a second. But roughly speaking, each dot in this picture corresponds to a Z mod 2 in the associated graded sense. It corresponds to map between two spheres stably. And the vertical line just means how decomposable it is in terms of a sequence of maps, such that each of them induce a trivial map on multi-coefficient homology. So the higher it is, the more decomposable it is in that sense. Okay, and you see that in this picture there is a periodic pattern near the edge. So that's the J part, which is roughly speaking 8-periodic. So these patterns are precisely 8-periodic, but there's a longer tower which is more complicated. So that's the contribution of the Balloony numbers. Okay, and there's also a gap in here. So this is actually part of the chromatic homotopy theory of telescope conjecture is predicting. So this picture is up to around 90 or 100. So if we were to have a picture, say up to 1,000 or even 10,000, we're supposed to see a bunch of other layers. So the whole picture is supposed to look like a rainbow. And there are a bunch of gaps, which is essentially saying that each dot in this picture should fit into a periodic family. Like the ones above are roughly speaking 8 periodic, but things in the second layer are correspond to things are detected by chromatic height 2, such as things like topological module forms. So for example, these two dots are connected by, detected by TMF. You will see, and TMF instead of periodic 8 is periodic 192. So you will see another dot instead. So this is 45, 45 plus 192. You will see another dot of this dot with increased filtration by 32, and see another copy of this dot. And it goes on forever, and so forth. And therefore, because of the slope, the whole picture should look like a bunch of layers, so like a rainbow like this. Oh, and by the way, our theorem about the 61 sphere is just saying that the 61st column here, there's no dots left. Okay. And of course, this picture is just the E-infinite page of a spectral sequence, and this is the E2 page. So the E2 page has a lot more dots. So if you're not familiar with spectral sequences, the way it works is on the E2 page there are more dots, and there are certain rules all the differentials has to satisfy, such as d squared 0, the Lamides rule, and other things. So these are the negative slope lines, and the way it works is both the source and target they cancels, and all the leftovers are the answers we're looking for. So this is the Adams spectral sequence. The E2 page is X over the Stigma algebra, but as you can see, a very interesting thing is that it doesn't have this gap in the middle, right? But it does have this gap in the E-infinity page. And the theorem regarding 61, there's just a lot of more dots on the E2 page, but eventually they all disappear. So the differential works goes to the left by 1 and goes up by 2 or higher. So these three are D2s, these reds are D3s, and so forth. Yes. And they're D4s, and yeah. So in my next talk, I will say more like details regarding just computing this spectral sequence. Okay. All right. So what do we know? So I'm gonna say a few words about the history. Serre used the Serre spectral sequence to compute all the unstable range into the stable range up to 8 stem. Toda used the EHP spectral sequence to compute up to 19 stem. And if we just want to compute the stable range, we use the two most popular ones, the Adams and the Adams-Novikov spectral sequence. What they have in common is that they both converge to the P primary part, and their E2 pages are both X over some Hopf algebra or Hopf algebroid. This one is based on the mod P cohomology, and the Novikov one is based on the complex cuboidal spectrum. So before I talk about these computations, here's a warning, which is stated as the Mahoward uncertainty principles. So the first Mahoward uncertainty principle states that any spectral sequence converging to the homotopy groups of spheres with an E2 page that can name using homological algebra, the previous two are such spectral sequences, will be infinitely far from the actual answer. So this principle essentially states that this problem of computing stable stems is not an algebra problem. It's not a homological algebra problem. If there's a spectral sequence, the E2 page is homological algebra, there will be infinitely many differentials we will have to compute. So when I first studied as a grad student, I was very fortunate, very lucky enough to be able to talk to Mahoward weekly for almost a year. So I asked him, what is the best method of computing the stable homotopy groups of spheres? So I was being lazy. I only want to learn the best method, so I don't have to learn all the literature. And his answer was, well, there's no best method. You really have to combine all the known methods together in order to push forward the known computation a little bit. And there goes the second Mahoward uncertainty principle, which states that any method that computes non-trivial differentials in such a spectral sequence will, again, leave infinitely many differentials undecided. So we really have to combine different methods in order to compute differentials. So the E2 page is pure algebra, but computing differentials is really the hard problem, which requires topological input. All right, so we have two spiral sequences. Well, let's compare them. So one comparison is there is the time reduction map on the spectrum level, which preserves pi degree. But this is not super useful in practice because it comes from two different filtrations. Whatever in here, they have different filtrations, so this map doesn't see it. But the good story is, well, it's more complicated. There's another connection developed by Hinz-Miller in his thesis. So there are two other spiral sequences. So the lower two are trigrided, so above two are bigrided, but they start from the same thing here. Okay, so this one collapses out at all primes. So one emphasis I like to make in this picture is that the above two are guided by the uncertainty principles. So we need topological input to compute differential in these two spiral sequences. But the lower two are purely algebraic. They start from some X group. They converge to X groups. We can even make computer programs to compute these all differentials in these two spiral sequences within any reasonable range. But by developing this Miller square, Miller was able to deduce purely Adams D2 differentials in here from purely algebraic data. So later on, we were able to use motivic homotopy theory to generalize this theorem. So let me speed up a little bit. So what we know at prime 3, we know around 108 stem. In prime 5, we know around 1000 stem. It looks very different, but if you plug in, they're both this number. And in this sense, at prime 2, we know a much larger range now. So I'm going to focus on p equals 2 computation. So Peter May, he sees this constructed this May spiral sequence, converts to Adams E2 page, and combining based on Toda's computation and Lamy through, he computed up to the 28 stem for the stable stems, the homotopy. So later on, Mahawar-Tangara computed up to 45 stem using various techniques. And also there's contribution by Bob Brunner using power operations in the Adams spiral sequence. So more recently, in 2014, Isaksen uses the motivic Adams spiral sequence over the complex numbers and gives the first rigorous arguments up to the 59 stem. I'll say how that works, but as guided by the uncertainty principles, he got stuck again. Guozhen Wang and myself, we developed this RP infinite method and computed only 2 more stems. But this method is too complicated to go further away. Then later, together with Bogdan Gheorghe, we realized there's another motivic method based on Isaksen's method, but very different. This is what we call the motivic Kervaire method. And together with Isaksen, we computed up to 90 stem with few exceptions. And more recently, together with Weinan Lin, there are some even newer methods, which we get a lot more progress after 90, but enough to determine what happens to the last covariant invariant problem in dimension 126. And here's, roughly speaking, the range before the recent work. So that's the range of Sayre, Toda, Peter May, and so forth. This very small column is 60, 61, and that's the motivic method up to 90 and beyond. All right, so I'm running out of time. Let me just say a few words of how the motivic method works. So SH is my notation for the stable homotopy category. So over any base field K, there is a stable infinity category or triangulated category or any base field K, so SHK. So in the classical case, there is a single graded spheres, but in motivic case, there are 2 types of spheres. One is the topological sphere. The other one is GM, the multiplicative group, which is just a fine line minus point. We call this S1, 1. We smash them together, we get P1. So as classically, when we invert things, we should invert both types of spheres in order to have a stable category. So one of the good things is that classically, the cohomology, the ordinary cohomology is a representable functor, and Wolski defines the motivic cohomology, which is also a representable functor in this motivic stable homotopy category. And upshot is that all the classical computational tools I mentioned earlier, the motivic versions, they all exist. And as for the reason there are 2 types of spheres, everything are bigraded. So we can define bigraded motivic homotopy groups and motivic cohomology groups, etc. Okay, and similarly, we can also define the motivic stable homotopic groups of spheres, which are bigraded now. So what do we know about these computations? So Morel decided that n comma n are determined by the Milnor-Ricci K groups by the work of Rawlings Spitzbach Ostsphere. N plus 1 comma n and n plus 2 comma n can be decided in terms of motivic cohomology, Hermitian Milnor K groups of the base field K. So in this sense, you can view the motivic stable homotopic groups of spheres as a generalization of certain arithmetic invariants of the base field. So that's as much as we know for general base field. And for a specific base field, we know a little bit larger range, and these are the cases we know of. So overseas, there is a particular interesting story, namely there is a Betti realization functor. If you take a algebraic variety over the complex numbers and we take the C points, we get a topological space. So we can extend this construction to the whole stable homotopic categories. So Wolski proves that the homology of a point, in this case, is more complicated. It's a polynomial ring with a generator tau in degree 0, minus 1. And by the way, this is essentially equivalent to Bloch-Kato, so this is a highly non-trivial theorem. So it turns out this map tau can be realized as a map between spheres stably, but we need to do some completion for it to exist. And under the Betti realization, it realized to the identity map classically. By the work of Dagger Isaksen, if we invert tau, you get back to the classical stable homotopic category at the prime. So in particular, if we can compute the bigraded motivic stable homotopic groups of spheres and we invert tau, we get back to the classical one. And this is exactly what Isaksen did to compute up to the 59 stem. Just as a comparison, he computed both spiral sequences and used this functor as a comparison, and the third degree can rule out certain possibilities of differentials. But then there's another interesting story, which is we just modeled out by tau. So it turns out there is a spiral sequence for it, just collapses, and as a result, its bigraded motivic homotopic groups can be completely described in terms of homological algebra. The interesting thing here is this bigraded homotopic groups, there's another motivic spiral sequence converting to it, which is highly non-trivial. There is a classical algebraic Novikov spiral sequence, which is also rather complicated and converts to these bigraded objects. So Isaksen computed the right-hand side up to around 60 stem. My collaborator Guozhen Wang made a computer program and computing the left-hand side around 45 stem. And when we compare the data, they have the same data, not just the abutments, but also the pattern of differentials on the E2 page. That shouldn't be a coincidence. In fact, together with Gheorghe, we prove that the above two spiral sequences are indeed isomorphic to infinity. So this turns out to be very useful in computations, but what is the theoretical reason for this? Well, it proves that there is an equivalence of stable infinity categories. And if you don't like that, think this just as triangulated categories. So left-hand side are just modules over this two-cell complex, which is the E-infinity ring. The right-hand side is the derived category of a certain abelian category, namely comodules over this Hopf algebroid mu star mu. By work of Quillen and Morova, this is also known as the abelian category of Cauchy coherent sheaves over the module stack of one-dimensional formal groups. So in this sense, this motivic theorem also built up connection to chromatic homotopy theory. So one way to think about this theorem is the following. We can view this element tau as a parameter of a deformation in the category sense. So in the middle is the motivic category. If we invert tau, that's the classical stable homotopic category as a generic fiber. And if we model by tau as a special fiber, this is a well-known, at least in algebraic topology, the derived category of some abelian category, which is purely algebraic. So having this deformation of categories, we can have this deformation of special sequences and use naturality to prove differentials this way. So here is the rough steps, how we do these computations. Many parts involves computer programs, but the ad hoc part is also consists. So we have this paper published over 100 pages, and and in the paper where that's only the ad hoc arguments, right? For all the free ones from a computer output, we didn't run anything. We just put the code there. So this new method can be used to reprove many hard differentials using this method. I listed 4 differentials proved using 4 different methods by 4 different groups of people. in particular, this one, by the two of us, about this 61 sphere, it took us 40 pages to write it down. But with this new proof, it's only a one-line proof. It's a computer output, right? Then naturality, and it's done. It can be also used to recompute early range very effectively. So I have some pictures. So this is a classical picture. I marked 6 differentials in low filtrations. And this is the motivic picture. This is completely computer output. So there is one D2 differential. It's purely algebraic. So 1 out of 6. There are 2 D3s. So 3 out of 6. 1 D4. 4 out of 6. One extension can be translated into a differential. So 5 out of 6. So this motivic method can compute 5 out of 6 harder differentials in the range up to 45. So that leaves one left, but that's okay. So it does not violate the second Mahauer uncertainty principle. All right, I'll stop here. Thank you.
Any questions?
Were there any errors in the earlier calculations that came up when you found more sophisticated methods?
Yes. In each round, when there's a new method introduced, there is always an error found in earlier computations. Yes.
And what about your new ranges? Are they verified by any other method?
So that's a great question. So the published version up to 90, now this new method can verify that. But the new method, there's no newer method, but it depends more on computer programs. So I would say in that sense, it's more trustworthy than human computations by hand. Yes. Yeah. Yeah. So this reminds me when I talked to Malcolm Howard, he liked to give me some exercises. And each time he give me a proof, I try to check all the details, and it doesn't work. And when I return, he give me another proof. So it seems to him that if you have more arguments, then you have more credibility of this fact must be true. But Peter May's advice to me was I should try to avoid this kind of thing. For every argument I write down, I should make sure it's absolutely correct. I think so far I was lucky to, but yeah. Yeah. Right. So cobordism just means you have two manifolds in dimension n. Cobordism is just the manifold in dimension n plus 1, whose boundary is just the disjoint union of these two manifolds. So complex means you want to have some sort of complex structure, but the dimension doesn't match, right? So therefore, it's a complex structure on the stable normal bundle. So when you embed into higher dimensions, you reach even dimensions as a normal bundle, then we requires a complex structure over there. Yeah.
Since that the basic realization is the bridge between the motivic part and the standard stable homotopy part. And I've also heard that there is, through the basic realization, there is a motivic version of periodicity. And I wonder if there are more properties that we can transfer between the stable homotopy part and the motivic part through this realization.
Right. So my understanding of your question is classically there's this real-bound periodicity, right? Motivically, there are actually several different objects. They all realize to this classical KO. So they have a more complicated pattern of periodicity because, for one thing, the homotopy groups are bigraded. And there has been many work studying completely compute the bigraded homotopy groups, motivic homotopy groups of these objects. So yes. And right, maybe related. So you could also ask this question for other base field, see if there are other connections. But the more direct one is probably the real numbers, right? If you realize the real thing, then you get a topology space with a C2 action. So it's a Galois group action. So there's also some direction over there, which we can do computations C2 accurrently, and we'll also do something R motivically. But for even more general base field, the connection is more indirect.
Okay, then that's it for